So, welcome to the most important topic of this module, guys, the linear approximation topic. It's not a very difficult concept, but I will have to emphasize on the importance of this concept, especially in the upcoming midterm. Let's recap a little. We were trying to in the very first parts of this module, we were trying to express the rate of change, right? And we figured out that the secant line from a point A to a point B was calculated, or basically determined by determining the slope of the gradient, right? The slope of this particular line, the gradient of this particular line that's forming between A and B, and the corresponding y values would just turn out to be B and f of B, right? And once that happens, we're basically going to result in a gradient for the given line, right? That was the idea. So the problem is that when we try to do this and we find the differential gets very close. The differential of this particular point gets very close to the tangent at that point. So if we are trying to find the equation of the tangent at that line, we can approximate that or get very close to that using the differential at this point by using the limit method or any other method by simply differentiating at that point. So that's the concept. This is the tangent line that we're talking about, right? That's the tangent line, and this is the secant line that we've talked about in detail in the previous videos of this module. So we know for a fact that f dash x naught is could be any point, and the differential at that point of the function x has to be equal to x approaching x naught for f of x minus f of x naught, right, divided by x minus x naught. And if you think about it, for x very close to x0 or x naught, the differential f dash x0 gets very close to the gradient of the secant line that we have just described above so elegantly. So if you think about it, we could just rearrange this equation, take this to the other side and rewrite this whole equation. We'd get f dash x naught times x minus x naught, right, roughly equal to f of x minus f of x0. So what do we get from this equation? Basically, if we take this to the other side, f of x naught, we get f of x, the function value at x, is approximately equal to the x naught value of x plus f dash of x naught times x minus x naught. And if you think about this for a second, this is very similar to the equation of the form y minus y1 equals m times x minus x1, which is the equation of the gradient. You could alternatively calculate this using the y equals mx plus c method as well, but I would probably go with this method because this is more official in a way. This is more like formal, something you might be able to use in the upcoming calculations, right? So once we're done with this, let's try to apply this concept to perhaps a tangent line. So what we would eventually result with, like using the same logic, is the equation y equals f of x naught plus f dash of x naught times x minus x naught. So basically, a linear approximation is going to be talking about using the tangent line, using the differential, right, to kind of approximate the value at the tangent line for a particular threshold point. So we mentioned at this point that why does this happen? This happens for very small values of x0, for values in which x is approaching x0, so the difference between the two is very less. So for that particular case, the differential is going to help us to determine this equation of the tangent line, right? And if we do a couple of examples, it's going to make more sense, obviously. So that's probably a good idea to do a couple of examples now. So in the first example, let's just write this down. We have a function f of x equals sine of x, right? So, and this is applicable for small values of x. That is completely fine, right? So we would like to use the value of sine at 0 to estimate the value of sine at some x very close to 0. So it's kind of like an open statement, but it's not that ambiguous if you think about it. We're trying to approximate the value of x very close to 0 for the sine function. We know what the sine function looks like, right? It kind of looks like this. So what we're saying is we need a kind of the equation of a line that can simplify values of f of x for small values of x0. So let's zoom in to that particular case over here. So what do we get? We get something like this, right? That's kind of like a zoom in of the sine function. So what they're saying is, for these small values of x, what if there was a line to approximate these values? And they're asking us exactly to do that. And that's not like a terribly difficult thing to do. All we have to do is set x naught, the thing we described in the upper part of this video, as 0, and we'd be done. But let's just write it down. So we know that f of x equals sine of x, right? And that is the same as saying 0 plus x, right? Because it's for small values of 0, right? With small values of x very, very close to 0. So the approximation of the tangent line in this case would be simply f of x naught plus f dash of x naught, x minus x naught, right? We know that from the above equation. And f of x is simply very, very close to f of 0, because 0 is the threshold point. 0 is the point around which I want my line to be concentrated. And f dash 0 times x minus 0 is going to give us that. So we know that f of 0 is what? Sine of 0 is 0, right? We know that. That's really not a problem for us. Well, what's f dash of 0? We know that f dash of x, the differential of that, is going to give us cos of x, right? And f dash of 0 is cos of 0, which is equal to 1. And 0 plus 1 times x is going to give us x. So what are they essentially saying over here? What they're basically saying is that for small values of x, fx equals x is a very good approximation for the sine function. So if you had a value like, I don't know, 0.0041, instead of plugging it in sine of x, what this function is saying is that you could do, all you could do is just plug in fx equals x, or f of 0.0041 in that value, and you could get 0.004, because that's a y equals x function, right? So for this, but this works only for small values of x, by the way. If you had a value of, I don't know, 60 degrees, or if I were to like speak in numbers, sine of 100, this wouldn't be applicable. Not at all, because what we suggested initially was that this worked for values of x very, very, very close to 0. So let's do another example to further solidify the concept that we've just learned. Let's consider the example in which we have 1.0000, and we have perhaps another 0, 5 zeros, 1, and we are raising this to a power 1, 0, 2, 3. Seems like a very weird question, right? It's not that weird if you think about it. We're going to simplify it. We want an approximation to this. They're just asking you to calculate this. But how are we going to do that? Well, it's not that simple. Not that simple to explain, basically, but it's a relatively simpler concept than the things we've learned so far. All we have to do is re-express this in some way that's going to be helpful to us. So what I'm going to do is, I'm just not going to consider this right now. What I'm going to say is, I have a function perhaps I have a function f of x equals x to the power 1023, right? And I'm going to try to find another function, maybe a line, maybe the equation of a tangent line that works for values close to 1, because 1.00001 is very close to 1, right, if you think about it. So if I use the exact same logic as I applied to sine x for values close to 0 over here, I could do the same for 1. So in this case, x naught just turns out to be 1. And if I use the equation that I've so eloquently written down in the above video, I would simply get this, right? And now all I need to do is plug in the values. For x naught is 1, right? So f of 1 plus f dash of 1 times x minus 1 is going to give me the answer. But what exactly is f dash of x? We have f of x equals to that, right? So we're just going to use the power rule here, and we're going to get 1023 times x to the power 1022, because of 1 is going to be subtracted. F dash of 1 is simply going to give us 1023, because 1 raised to the power, well, a million would give us 1. It won't change anything, right? So that's just like playing along with it. And what does f of 1 give us? F of 1 gives us the exact same thing, 1 to the power 1023. So what I'm getting over here is 1 plus 1023 times x minus 1. So how is this helpful? Let's try to express this. 1 plus 1023 times x minus 1 is going to give me the answer. But this is the value for f of x. What am I trying to plug in over here? Well, think about this for a second. What am I trying to plug in over here? Well, I'm trying to plug in this value, because this is a value very, very, very close to 1. And this function, or this line, works for values close to 1. So let's just plug in what we're trying to determine. And we're simply going to get 1 plus 1023. And if we subtract 1.123451 minus 1, we're simply going to get 1 plus 1023 times 0.000001, right? Because 1 subtract over here. And this just gives us what? Well, if you were to simplify it, you get 1.001023. Because all that happens is it's just 10 to the negative 5, I think, right? So you just multiply that by, you just move it and just add it up to 5 decimal places. And that's the approximation. So a relatively simpler concept. It's not that hard to understand. All you need to do is understand the examples that we've conducted so far and apply them to different scenarios to be able to understand this. In the next video, we're going to be closing this section by talking about the differentials and approximation part of this. It's an extension of the same topic, right? So hopefully I'll see you there.